Exponents are used to show that the same factor is used several times. For example, if we have 5 times 5 times 5, we have 3 factors of 5, which can be indicated using the exponent 3. So the 5 is called the base of the exponent, the 3 is the exponent. The exponent tells us how many times the base is used as a factor. That's all there is to it. Now, these two look pretty much the same, except this one involves a parenthesis, and I'm illustrating here the most commonly made mistake in dealing with exponents. In this situation, the negative 4 is the base of the exponent. So we have 2 factors of negative 4. This really means negative 4 times negative 4. Or plus 16, positive 16. Here, this is the negative of 4 squared. Only the 4 is squared here. So this is the negative of 4 times 4. So this is negative 16. Big difference here. It's important to identify the base of the exponent. By the way, the exponent is read as a power, or sometimes there's a kind of a nickname for the exponent. I read this as 5 to the 3rd power, I think, a few moments ago, and that's fine. But a 2 and a 3 have kind of special names. A 2 is called squared, 3 is called cubed. So this could be read as 5 cubed. Let's talk about some properties of exponents. We recall that when you multiply like bases, you add exponents. So x squared times x cubed is x to the 5th, and after all you're doing here is indicating that we have 5 total factors of x. This says we have 2 factors of x. This says we have 3. Altogether, we have 5 factors of x. When we divide like bases, we end up subtracting exponents. Fundamentally, we can think of this answer as x to the 7 minus 4. 7 minus 4 is 3. And that only makes sense because these 4 factors of x are canceling with 4 of the 7 factors of x in the numerator. So no wonder we get x cubed. A negative exponent implies a misplaced base. Basically, this x to the negative 3 means 1 over x cubed. It could also be written as 1 over x all cubed like this and would say the same thing. A 0 exponent on a base is simply a factor of 1. And it really doesn't make any difference how complicated this base is. This could be, 7 n cubed x, and if all of it is raised to the 0 power, it's still just 1. When we have an outside exponent and in parenthesis we have more than one factor, then this exponent applies to each factor separately. This is 5 squared times x squared, or 25x squared. Same idea with fractions, which we'll see in a minute. Here we have a certain power raised to a power, and when that occurs, there are a couple of ways of thinking about it. The most fundamental way is to say we have 3 factors of this. And if you wrote x squared times x squared times x squared, you would see that we get x to the 6th power. The shortcut here is that when you raise powers to powers, you multiply the exponents. So this is x to the 2 times 3, or x to the 6th. When we have an exponent applied to a fraction, as I mentioned a moment ago, the outside exponent applies to each of the numerator and denominator separately, or we can think of it like that. And we could think of this as 2 over x times 2 over x times 2 over x. You see 3 factors of that. But it's sometimes valuable to understand that we can apply the exponent separately. So we would think of it kind of like this, and then the 2 cubed would give 8. If we had an outside exponent that were negative, then the technique often is to just flip over the fraction. After all, when that negative idea is applied to each of these separately, we're talking about misplaced base, misplaced base. So if it's in the numerator, it belongs in the denominator. If it's in the denominator, it belongs in the numerator. That's what I mean by misplaced. So the technique to deal with an exponent that's negative applied to a fraction is just flip the fraction over, and then apply that exponent separately to numerator and denominator. We get x cubed over 8. Let's do a few problems. Here we're just multiplying, and in multiplying like this, we multiply numbers times numbers and like letters times like letters. And that's the way you kind of want to separate your thinking in problems like this. We have negative 3 times 4, that's 12. And then a times a squared. Now, all I'm doing is adding the exponents, and the exponents on a are understood to be 1s. So I'm just adding 1 and 1 to get this a squared. B to the 4th times b to the negative 3. Well, this really means that this b base should be in a denominator. And we could actually write a separate step to have 4a over b cubed, and then look at the cancellation of the b cubed, or the 3 factors of b with 3 of these 4 factors of b. But a nice way to do it here is to just say, well, when multiplying like bases, we add or collect the exponents. So this is b to the 4 minus 3. Oh, that's simply b to the 1 power, or simply b. Here the cubing applies to every different factor inside the parenthesis. So we're cubing the 2. That's 2 times 2 times 2. That's 8. And then x cubed, and then y to the 6th. Now when you hit the letters, now with the number, it's 2 cubed, you see, so we get 8. But when you hit the letters, you think about that technique of raising power to power, so you multiply the exponents. The understood exponent here is 1, so 1 times 3, 3, and then 2 times 3, 6. That's the fast way to work it. When negative exponents are involved in one or more factors that are within the numerator and denominator, I recommend you burn a step and move those factors to a more appropriate location. That is, we think here that this negative exponent implies a misplaced base. The base of this exponent is x. So we kick the x up into the numerator and we get x squared over 3. And from here, we're already in simple form, so we need not do anything else. In a more complicated problem like this, though, the technique looks like this, that we see negative exponents on individual factors, so we'll burn a step and just move the factors around a little bit. It works like this. The 12 stays where it is. The a cubed I'll bring down. It stays where it is. It's positive. And let's see, the b to the negative 4, I want to move this downstairs, you see. Now the 4 stays where it is. The a to the negative 2 is going to move upstairs. This b is going to stay here. You see, these are the factors that stay put. And now I'm just taking this b to the negative 4, throwing it downstairs. It becomes b to the 4th. This a to the negative 2 goes up to become a squared. And now it's pretty easy to see through the rest of the problem. The 4 and the 12 cancel, leaving 3 in the numerator. I've got, let's see, this a cubed times a squared is a to the 3 plus 2, 5. And for the b's, b to the understood 1 times b to the 4th, 1 plus 4, 5. So this is b to the 5th. In this one, we have the outside exponent is negative. And that exponent applies to a fraction. So we're going to burn a step and flip the fraction over. So just flip this fraction over, and it'll change that the sign of that exponent. So we'll have y over 3x squared. And now this outside exponent applies to every different factor that we see. So square y, and we get y squared. Square 3 to get 9. Square x squared, and we get x to the 2 times 2, or x to the 4th. Scientific notation is a technique for writing incredibly large numbers or incredibly small ones in a more efficient way rather than using all of those zeros. It's a technique where we use a number fundamentally between 1 and 10 and then times 10 to some exponent. For example, a number like 93 million can be written as 9.3 times 10 to some exponent, and we identify the exponent on 10 by noticing how many digits over which we need to move the decimal point. Now the decimal point is understood to be here in 93 million, and we're moving it to a position between the 9 and the 3. So we're moving it 3, 6, 7 positions, and therefore this is 9.3 times 10 to the 7th power. And for incredibly small numbers, we're moving the decimal in the other direction, and it just means that the exponent on 10 is going to be negative. But here we're going to move the decimal point to a position between the 4 and the 6. So we're moving it to this position, and we're moving it therefore 1, 2, 3, 4, 5, 6 places. So our number in scientific notation is 4.6. 4.6 times 10 to the negative 6. Now, your calculator, by the way, knows all about scientific notation. You might put 93 million into your calculator and press the mode button and then make the selection from, let's see, I think it's from normal to scientific, SCI. And it's right at the top of that display, and then go back to the main screen and press enter on 93 million, and it'll write it in scientific notation. Either E or double E are used in that kind of notation. For the TI-83 Plus, it's written on the calculator as 9.3 E 7. I think, yeah, that's the exponent on 10. But the number following the e is the exponent on 10. All right, to go in the other direction, that is to write a number that is in scientific notation in its expanded form, all we do is perform the indicated operations. Here we're multiplying 4.25 times 10 to the 5th, and when we multiply by powers of 10 like this, we're just sliding the decimal point corresponding with the exponent on the 10. So we're going to slide this decimal point 5 places to the right. This becomes 4, 2, 5, let's see, 1, 2, and we need placeholders for the other 3. So this is 425,000. When we have a negative exponent, we're just sliding the decimal point in the other direction. After all, this means, let's see, the negative exponent means misplaced base, so actually this would be 10 to the 6th down in the denominator, you see. So we're dividing by 10 to the 6th power, which is the number 1 with 6 zeros. And if we're dividing by a number which is 1 followed by 6 zeros, we're sliding this decimal point 6 places to the left. So let's see, we want the number to be written like this, and 0 point, and then some zeros, and then 1, 2. Well, how many zeros do we need? Well, let's see, we slide 1 here, and then we need 5 more. So I'm going to tack on those 5 zeros right here, and then the 1 and the 2. So this is our number in sort of an expanded form. Take a look at this pattern. This pattern involves numbers that can be written as multiple factors. We're going to get into a little discussion or a little reminder about radicals here. And this pattern, I think, will help us with the idea. 9 can be written as 3 squared, and the equal factors are 3 and 3, 3 times 3. So 3 is said to be a root of 9, and it is a square root of 9. It is a square root of 9 because it is one of 2 equal factors. You see, 2 equal factors implied by the squaring idea, square root, you see. Okay. 25 is negative 5 squared. I want to make sure we understand that a negative number can be a square root. Now, we'll talk about the radical and its implication in just a bit, but 25 is negative 5 squared like this. Negative 5 is used as 2 equal factors, you see, to give 25. Negative 5 is a root, and it is a square root. Now, 64 is 4 cubed. 4 is used as a factor 3 times. 4 is a root, and it is a cube root. It is a cube root. It is a root, you see, because of this equal factor business. It's a cube root because 4 was used as a factor 3 times to give 64. All right, 16 is 2 to the 4th power. 4 factors of 2. 2 is a root. It is a 4th root of 16. 25 is 5 squared. It's 5 times 5. 5 is a root. It is a square root. Now, I'm showing the 25 twice because I want to make it abundantly clear that there are 2 square roots for 25. Now, the request for roots is made by using a radical sign. The radical sign looks like this, as you recall, and this is read as the cube root of 27. This little squiggly thing is called a radical sign. The number under the radical sign is called the radicand, and this number up here is the index of the radical. Now, when no index is written, it's understood to be 2. This whole business is called simply a radical, with the radical sign, radicand, and index, just a radical. Now, the radical can be interpreted in this way, that when we look at this, it is a request for a number, a factor that is used 3 times. It's a request for one of 3 equal factors within 27, and that number would be 3. The cube root of negative 27, what is one of 3 equal factors that gives negative 27? Well, it's negative 3. And for the square root of 25, well, gee, we found earlier that there are really two square roots of 25. And when there's a choice like this, we're talking about here, this is the request for the principal square root, or the positive square root of 25. So the square root of 25 here, as we write this, or as we interpret this, is simply 5. If we want the other square root of 25, it's requested like this, as the negative of the principal square root of 25. So that would give us negative 5. Quite a bit of difference now when this minus sign appears under the radical sign. When we're taking the square root of a negative number, it's a request for one of two equal factors that gives negative 25. Is there such a number that we can multiply times itself to give negative 25? No. So there's no real number that will meet this request. So generally speaking, we can take an odd indexed radical of either positive or negative numbers. But when we're talking about an even indexed radical, that is square root or fourth root or sixth root, then we take only those roots on positive values. If we're talking about negative values under an even indexed radical, we don't get a real number as the result of that request. Have a look at these two problems. Here we have the cube root of 8 squared, and here we have the cube root of 8 squared. Apparently, on 8, we are both cube rooting and squaring, and it turns out that it doesn't make any difference which of those two operations we perform first. Let's look at it both ways. We have, let's see, under the radical we have 8 squared. Well, that's 64, but the cube root of 64 is 4. Now here we have the cube root of 8, which is 2, and we're squaring 2 to give 4. So these two are equivalent forms. We can go from one to the next. And if you have the choice between these two, it's this one that you'd like to choose, because after all, you're dealing with much smaller numbers if you take the radical on the radicand first. If you can do that first, then that's what you'd like to do, because you'll deal with smaller numbers. In fact, if you're in this form, sometimes it's valuable to go to that form and work the problem. Here are some properties of radicals that we bumped into in the past. The square root of 2 times the square root of 3 is the square root of 6, and generally the square root of a times the square root of b is the square root of ab. Now, that's not true when a and b are negative, but it is true when the radicands are positive. And when the radicands are positive, that's the only situation that makes sense for us. So when these radicals make sense, we can do that kind of thing. All right, the fourth root of 27 over the fourth root of 9, if we have the same indexed radical in both the numerator and denominator, then we can think of this as that same indexed radical applied to a fraction composed of those two radicands. So we have the fourth root of 27 over 9, which is the fourth root of 3. And just a technique for simplification. If we have kind of a radical within a radical, we can multiply the indices. This is the cube root of the square root of 5. Just multiply the index here times the index here. Understood 2 times 3. That's the sixth root of 5. Now, let's talk about kind of undoing the situation. You know, squaring and square rooting are sort of inverse operations. They tend to undo one another. Cubing and cube rooting would tend to undo one another. So it kind of makes sense that if we have the cube root of 5 and then we're cubing the cube root of 5, we would get 5 back. After all, this is a request for a number which can be used as a factor 3 times to give 5. And we're taking this number that can be used as a factor 3 times to give 5, and we're using it as a factor 3 times, you see. No wonder we get 5. All right, now, take a look at this. The square root of 5 squared. Again, the same fundamental idea, we get 5 as a result. There's just one little tricky situation here. What if we had the square root of negative 5 squared? Would we get negative 5? Well, no, because this doesn't make sense to begin with. You see, that we can't take the square root of a negative number in the real number system. So this just doesn't make sense. However, this makes sense, that makes sense, and more generally, the nth root of any number a raised to the nth power is a, generally. Now, we have to make sure that this part of it makes sense when we have an even indexed radical. The a value can't be negative, you see, when we have an even indexed radical. So, now let's talk about the situation where we're taking the nth root of a to the n like this. Now notice the difference between these two is that we're raising this a to the nth power before taking the radical. And here we're applying that outside exponent after taking the radical, after figuring the radical. Now, it may seem to be the case that it doesn't make any difference here, but it makes a little bit of a difference, and we're going to look at a few cases. So we're just investigating whether or not this is going to be the case. Let's see. Consider cube rooting. We have the cube root of 5 cubed. Well, 5 cubed is 125, and the cube root of 125 is 5. That works out just fine. So the cube root of 5 cubed is indeed 5, you see. That's the idea. And we're investigating to see if generally the nth root of a to the n is always going to be a. That's what we're trying to find out. All right, how about making this radicand negative, this part that is raised to this exponent? We've got, let's see, the cube root of negative 5 cubed. Negative 5 cubed is negative 125. The cube root of negative 125 is negative 5. So it seems to work out in this situation. Let's go to an even indexed radical. We have the square root of 5 squared. 5 squared is 25. The square root of 25 is 5. Gee, it seems to work out just fine here. Look at what happens, though, when the 5, the number squared, becomes negative. Now, you might say, well, we can't take the square root of a negative number. Well, we're not taking the square root of a negative number because the negative value here is being squared, you see, before we apply the square root. So negative 5 squared is 25, but the square root of 25 is 5. And these don't match up. So it is not the case that generally the nth root of a to the n power is going to be a. We have to split it into cases. Here's how it works. For n odd, the nth root of a to the n is a. As long as n is odd, we're fine. But when n is even, you see, we have the possibility of that sign changing. So we have to say that the nth root of a to the n is going to be the absolute value of a. Here, for example, I mean, this is a good example of the situation that the n is even here, and we have the negative value squared. It becomes positive, and we have a positive value. We have the absolute value of the number we started with here. So here's how this is illustrated. Now, let's go through a couple of examples. Here we have the sixth root of y to the 6th power. So we have an even indexed radical. We have the same number here, the same exponent as we have as the index of the radical. They seem to negate one another. But since we have evenness in both cases, the answer is really the absolute value of y. Because y could be y could be positive or negative. When we raise to the 6th power, it's going to be positive, and therefore we get a positive result. So we always get a positive result in this situation. Now, on the other hand, when these two numbers happen to be odd, it doesn't matter whether this number is positive or negative. It's going to come out to be the same over here. You see, we raise, if it's negative, for example, a negative number to the 5th power, a negative number. But the 5th root of that negative number is going to be negative. So we're okay with that situation in this circumstance. Let's look at simplifying. When simplifying square root and cube root particularly, we subdivide our radicand into, if we're talking about square rooting, into squares times leftovers. Here, we can take the square root of squares, and so we factor this in such a way that we have squares times leftovers. So we're looking for the largest square in 75, and it's 25. So we factor 75 into 25 times 3. And then we look for the largest square in the literal part, the letter part. In x cubed, x squared is the largest square, and we have x as a leftover factor. Now we can take the square root of 25, it's 5. The square root of x squared is x, and left under the radical would be the 3x. So this then would be our answer. Here, the same idea. 4th root of all of this. We want to separate this into, let's see, things to the 4th power times leftover things. Now let's see, I see that this is even. Maybe this has something to do with 2 to the 4th power. Let's see, 2 cubed is 8, 2 to the 4th is 16. Okay, is 16 somehow in here? Well, is this 16 times 3? Yes, so we have 16, which is 2 to the 4th power, times 3. And then x to the 4th, well, gee, x to the 4th, we can take the 4th root of x to the 4th. So now the 4th root of 2 to the 4th is 2. The 4th root of x to the 4th is x. And left under the radical is the 3. So we have 2x times the 4th root of 3. Now, we got a little problem here, though. What would have happened if x was negative? See, if x were negative, you see, negative whatever to the 4th power would be positive. We still have a positive number here, so it would be okay to make the calculation. And yet, we don't get x out here. This x is certainly not negative, because when we raise to the 4th power, you see it's going to be positive. So, and the 4th root of that number has got to be positive. So we have to assure ourselves that this is a positive number. So we do that by doing this. Now, we didn't have that problem up here. We did take the square root of x squared, but the original problem had x cubed in it. So this x, if it were negative, a negative number cubed would make this radicand negative, and therefore the whole problem wouldn't make sense, and we couldn't do it to begin with. So if this makes sense, you see, then x must be positive, and therefore it's okay to write like our answer like this. It's just a tricky little situation that we have to look out for from time to time. For cube root, same idea. We are separating our radicand into cubes times leftovers. Now the largest cube in 40 is 8, and we factor 40 into 8 times 5. And then the largest cubed in x to the 4th is x cubed. So we factor this way. And then the cube root of 8 is 2. The cube root of x cubed is x. And left under the radical is 5x. And that's all there is to it. Same idea here. And the negative business doesn't bother us at all when we're talking about cube root. So we have the cube root of, let's see, cubes times leftovers. The largest cube in negative 250 would be negative 125. And it's negative 125 times 2 to give negative 250. All right, so we factored here. What about here? Well, the largest cube in x to the 7th is x to the 6th. And we have a one leftover factor of x. Now, the cube root of negative 125 is negative 5. The cube root of x to the 6th is x squared. Because after all, x squared to the 3rd power is x to the 6th, you see. And then left under the radical is the cube root of 2x. You may recall that like terms can be brought together, and in the past, like terms would mean terms having the same letters and the same exponents on those letters. And in those circumstances, we can collect coefficients in order to collect like terms. Well, when terms involve radicals, the terms become alike when we have the same index of the radicals and they also have the same radicand. Let's take a look at a problem. Now, these two are not like terms. The indices are the same, but the radicands are certainly not the same. Best we can do right now is to simplify the two terms involved here and just see what happens. Well, we would go through the process of simplification by thinking about taking 48 and factoring into square times leftover, and the largest square in 48 is 16, and the leftover factor is 3. Now let's stay with this term for a couple more steps. The square root of 16 is 4, and that 4 factor goes outside of the radical, and the 3 is left under the radical. The 2 times 4 is 8, so here we have 8, the square root of 3. Moving over to the other term, we have minus 3, and then the largest square in 27 is 9, so 27 is 9 times 3. This 3 we bring down. The square root of 9 is 3, giving us another 3 factor outside of the radical. This 3 remains under the radical, so we have this. Now, minus 3 times 3 is minus 9, the square root of 3. And now we have like terms. Same index, same radicand, you see. It's as though we have 8x minus 9x. And in that case, we have negative 1x, or simply negative x. Well, here we have 8 of these things minus 9 of these things, giving us negative 1 of these things, or simply negative the square root of 3 for our answer. Here's a problem, same idea for our concept. That is, we want to just simplify here, and see if we have like terms in order to collect. Now, under the radical, we're looking for a factorization which is cubes times leftovers. So we have cube times leftover. This is the idea. The largest cube in 16 is 8. 16 then is 8 times 2. And the largest cube in x, there aren't any cubes in x, so we put that x factor over here. Now let's again stay with this term until we have it in simple form. We have 5x times the cube root of 8 gives us a 2 factor outside, and left under the radical will be the 2x. Now, the 2 times 5 is 10, so we have 10x times the cube root of 2x. For the other term, we factor into, well, let's see, cubes times leftovers. The largest cube in 54 is 27. 54 is 27 times 2. The largest cube in x to the 4th is x cubed. So it's x cubed times x for the factored form. Now we factor, let's see, the cube root of 27 is 3. The cube root of x cubed is x. And left under the radical is 2x. I'll just bring this down to put it on the same line as the other part over here. Now take a look at the two terms. Are they like terms? Go like this. Yes, they are like terms, because not only do we have the same index here, same radicands, we also have the same variable factor here in both terms. So it's like we have 10 of these things, and we want to subtract 3 of these same things. You see, and all we do is collect those coefficients then. So 10 minus 3 gives us 7 of these things that are x, the cube root of 2x. An interesting technique involved in simplifying radicals is the idea of rationalizing. And rationalizing is the technique of removing radicals from denominators, basically. And that technique involves this. If we want to rationalize this, that is, clear the radical from this denominator, we'll create a situation in the denominator where we can take the square root of a square, you see, and therefore the radical will disappear. Now to do that, we go through a little question and answer process like this. We ask ourselves, what's the smallest square that 3 goes into? Well, that would be 9. How many times does it go? It goes 3. So we need a 3 factor in here. So we're going to inject that 3 factor into the denominator by multiplying it in like this. We're going to multiply by the square root of 3 in the denominator. But if we multiply by the square root of 3 in the denominator, we have to multiply by the square root of 3 in the numerator as well, because we need to multiply by a form of 1. And when we multiply by a form of 1, we are changing the form of the fraction, but not its value. Okay, so that's what we want to do. Change the form, but not the value. In doing that, we have the square root of 9 in the denominator, but we can take the square root of 9, it's 3, and this then becomes 2, the square root of 3 over 3. So this denominator has been rationalized. It has been removed from the denominator. Here we want to rationalize. We have a cube root situation. We want to create a condition where we have the cube root of a cube. So we ask ourselves, what's the smallest cube that 5 goes into? It's 125. How many times does it go? It goes 25 times. 5 into 125, 25 times. So we're going to multiply by the cube root of 25 in the denominator. And if we're doing that in the denominator, we have to do the same thing in the numerator, because we need to multiply only by a form of 1, changing the form of the fraction but not its value. All right, in the numerator we have 2, the cube root of 25. In the denominator we have the cube root of 125, which we can simplify into simply 5. So we bring over the numerator 2, the cube root of 25. In the denominator we have simply 5. When binomials are involved and we have a radical in either or both terms of the binomial of the denominator, then we rationalize by multiplying by the conjugate of the binomial. Now the conjugate is the same binomial with a different sign. That is, the conjugate of 2 minus root 5 is 2 plus root 5. And so we're going to multiply in the denominator by 2 plus root 5. And in the numerator, therefore, we're going to multiply by 2 plus root 5. A really neat thing happens when we multiply the sum of terms times the difference of the same two terms. Remember, the middle term goes out in this situation, and we get the difference of squares. You may recall that from an earlier algebra course. But if we don't even remember that, we can use the FOIL method here to multiply. That's what I'm going to do here, at least for our first example. So in the numerator, we have 3 times 2 plus the square root of 5. I'm going to leave it in factored form like this because I'm looking for a cancellation opportunity at the end of the problem. And in the denominator, I'll multiply this out. Now, using the FOIL method, 2 times 2, 4. 2 times root 5 is 2 root 5. Then minus root 5 times 2 is minus 2 root 5. And minus root 5 times root 5 is minus root 5 squared, or minus root 25, if you'd like to think of it like that. But at any rate, the 2 root 5 minus 2 root 5 go out, and we have 4 minus, well, remember, this part, root 5 squared, is simply 5, so this is minus 5. So we have 4 minus 5, which is negative 1. So we have 3 times 2 plus the square root of 5 over negative 1. Now, this minus sign can float. You know, if we have a fraction, there are really 3 positions for signs. We have the sign of the numerator, the sign of the denominator, and the sign of the fraction itself. If we have one minus sign, you see, then it can float to any of those 3 positions. And here it's convenient to allow the minus sign to float to the numerator just to make it, to write it in a little bit simpler form. So we have minus 3 times 2 plus the square root of 5 as the answer. Now, back here, we could have performed this multiplication rather quickly. We could have thought about it as, well, let's see, we're multiplying the sum and difference of the same two terms. We get the difference of squares, so it would be 2 squared minus root 5 squared like that. We could go right to that step if we want to and simplify maybe a little bit faster than before. There is a situation in calculus that calls for us to rationalize numerators. Now, this is not part of the simplification process for radicals. When radicals are involved in expressions and we're rationalizing in order to simplify, it means we're clearing the radicals from denominators. We just generally want to do that when we're simplifying and the problem involves radicals. Well, in calculus, though, there's a special situation where we want to clear the radicals in numerators, and that process works like this. And it's very similar to the concept that we were looking at before. If we're rationalizing the numerator, we want to clear the radicals from the numerator, then we multiply up here by the conjugate. The conjugate would be the same binomial with a different sign. So we're going to multiply in that numerator by the square root of 5 plus the square root of 7. And if we multiply by that amount in the numerator, we have to multiply by the same amount in the denominator, so as not to change the value of the fraction, but only to change its form. All right, parenthesis around all binomials will help us with the multiplication. In the numerator, we have root 5 times root 5, root 25. Root 5 times root 7, root 35. Minus root 7 times root 5 is minus root 35. Minus root 7 times root 7 is minus root 49. In the denominator, 2 times binomial, left in factored form for a cancellation opportunity later. Root 35 minus root 35 take each other out. Root 25 is 5, root 49 is 7. So we have 5 minus 7 in the numerator, or negative 2. The 2's go out here, and we have simply negative 1 over root 5 plus root 7 for the answer. Radicals can be indicated by using fractional exponents. For example, the square root of 3 can be expressed as 3 to the 1/2 power. The important idea here is that the denominator of the fractional exponent corresponds with the index of the radical. Now, our ability to move from fractional exponent form to radical form and from radical form to fractional exponent form allows us to simplify in certain situations. For example, here we have a factor where we have a radical, and we can change that radical form into fractional exponent form like this. The 4, the index of the radical, will become the denominator of a fractional exponent. The 3 here is the power on x, and it'll be the numerator of that fractional exponent. So this factor can be expressed as x to the 3/4 power. Now we have, let's see, x to the understood 1 times x to the 3/4. Multiplying like bases, we add the exponents, so we can add 1 3/4 to get x to the 7/4. If we have a base raised to a fractional exponent, we can really think of this as having two operations applied to the base. That is, here we have squaring and cube rooting applied to the 8. And we can think about applying either of them first. That is, we can think of this situation as the cube root of 8 squared or as the cube root of 8 squared. You see squaring first here, squaring after the cube rooting in this situation. Now, either way, we get 4 as the result. The cube root of 8 is 2. 2 squared is 4. Here, 8 squared is 64. Under the radical, the cube root of 64 is 4. In this situation, we can go to a radical form by thinking, well, let's see. We have 4 is the denominator of this fractional exponent, so 4 is the index of a radical. So this is the 4th root of y cubed, and this is the 4th root of z. Well, let's see, we have 4th roots in both of these, so we can just multiply those radicands. So this is the 4th root of y cubed z. Here we have x to the 2/10 power. Well, we can think of this as a fractional exponent. Gee, 2/10 is 2 over 10 or 1/5, but that is the 5th root of x. So we can just change form, just kind of massage the situation here, and sometimes really get a good simplification of the situation. Here we have negative 32 to the negative 4/5 power. We have a lot of things going on here. And it's important when you're looking at a problem that seems to have a good bit of complication, as I think this one does, that you just pick off one situation at a time. Just do one thing at a time that you're sure of. Now, we can choose to do quite a number of things here. We could apply the 5th root here to the negative 32, or we could deal with the negative exponent. Now, do understand that this minus sign and that one are not even distant cousins. They have nothing to do with one another. They indicate entirely different things. This is saying we have a misplaced base, and this is the opposite of 32. You see, so, all right, let's just be sure of what we're going to do first. I'm going to deal with the fractional exponent. I'm going to just kick this base into the denominator. So this is just one interpretation. Now we can go into the radical form and think about the 5th root of negative 32 to the 4th power. Now that 4th power business, that 4 can either be kind of under the radical here or sort of outside. We'd like to, I think, take the 5th root of negative 32 first before we raise to the 4th power. After all, if we raise negative 32 to the 4th power, we'll deal with an incredibly large number here. So let's kind of think about it like this. All right, and therefore, let's see, we'll get the 5th root of negative 32 turns out to be negative 2. So this is negative 2 to the 4th power, and negative 2 to the 4th power is 16. So this is 1/16. Here we have the 9th root of a cubed. Let's go from the radical form to the fractional exponent form. And when we do, we have 3/9, which reduces to 1/3, which we can go back into radical form with as the cube root of a. So we create a simpler radical by just going into this other world, this fractional exponent world, and coming back out to the radical world, and we have a simpler radical. Here's one of my favorites. It's where we have a radical situation in a nested configuration. Now, there are really a couple of ways to look at this. We saw, I think, earlier that we can multiply the indices here. This is really the sixth root of 125. That is a way to look at it. But I want to show you another way to manipulate here. We can think of this as the cube root of, now, think of the square root of 125 in the form of a fractional exponent. This is really 125 to the 1/2. And now think about this. This cube rooting business indicates a fractional exponent. So this is really 125 to the 1/2 to the 1/3. You see, and this is then 125 to the 1/2 times 1/3. That's 1/6. And this is really then the sixth root of 125, which we could have seen from the very beginning. All right, just a lot of manipulation here. Actually, we have an opportunity to simplify a bit because 125 is 5 cubed. So we can think of this as the sixth root of 5 cubed, but let's go back into the fractional exponent form. This is 5 to the 3/6 power, but 3/6 is 1/2. So this is 5 to the 1/2, or the square root of 5 in simple form. Now we could have arrived at the square root of 5 a lot sooner had we taken a different tactic here and manipulated the 125 as 5 cubed a little bit early on. But I just wanted to show you a lot of different manipulation opportunities here with the problem.